Hello, 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 and welcome back to Shiksha Acosta. Today we're going to learn how to about the applications of similar triangles. So in this lesson, we're going to learn how to use these ideas of similarity and congruence to solve problems that show up in real life. And you're successful when you can actually do that, when you can solve problems that involve similar triangles in realistic situations. To start us off, I'd like you to take a look at these three diagrams and ask yourself, in each diagram, which are the corresponding sides and which are the corresponding angles? Pause the video here and see if you can figure that out. Let's look at the first diagram, obviously. First, I'm going to take a look at at side length AC down here. And I can see that this large triangle here, in triangle ABC, is similar to this triangle over here. And side length AC would then correspond to side length DC from the smaller triangle. If we follow that pattern, side length AB is similar to side length DE. And finally, side length BC is similar to side length EC, or it corresponds to it. This is the symbol for something corresponding to another value. Now that we have the side lengths down, let's take a look at the angles. So over here, we have an angle over here that is actually shared between both similar triangles. And so this angle here, which I'll call angle ACB, that angle it corresponds to angle DCE. Those are the exact same angle. Continuing on, this angle and this angle, therefore, are the ones that correspond. So ABC is corresponding to DEC, excuse me. And finally, the right angle down here in the corner, this is angle BAC, and that corresponds to angle EDC. In our next diagram here, we've got two triangles. They're meeting at this point right here. And in fact, this side would then correspond to this side. So AB corresponds to ED, not DE. We always try and go in the same order. AC then corresponds to EC, and BC therefore corresponds to DC. And looking at the angles, these two angles are opposite each other, and therefore they are equal and corresponding. The right angle here is corresponding to the right angle here. That one's also pretty easy to see. And of course, this one then therefore corresponds to this one. In our last diagram, this one's a little trickier because there's actually lots of different triangles happening over here. So just to start off, side AB corresponds to side DE. You can see that this is a smaller version of this triangle. But it also corresponds to a bunch of other sides. Notice that this triangle is also a miniaturized version, and therefore it also corresponds to side AF, as well as this one to side FB. And finally, there's another triangle here that's upside down, but we already have that noted as side DE. Now let's go to just do some angles before we go on to the other sides. So if we are looking at this diagram over here, this triangle here, let's say this angle ABC. Notice that that is also shared with this smaller triangle, and so therefore angle FBE is exactly the same. It's also the same as this angle up here, angle DEC, as this angle over here, angle AFD. And because this triangle is the same as this triangle but flipped upside down, we can imagine that this angle would have ended up right over here. And so that's angle EDF. Now, taking a look at some of the side lengths that are sort of going this way. So this is side BC, and that's the same as side BE, or it corresponds to side BE from this triangle. This one and this one both correspond, and this side length therefore corresponds to this one. It also corresponds to this side over here, so that's side EC, to this one, side FD or DF. FD, because it's going in this direction. We want to keep that consistent. Now taking a look at some of the angles, going back to those, if I look at angle BCA, this one right up here, that's the same as angle ECD. It's literally the exact same angle. This is just a smaller triangle within the larger one. But of course, we can see this angle all over the place. It's right over here at BEF. It's right over here at FDA. And finally, it's right over here. And if this was upside down, that would be DFE. Our final side length over here, this is side length CA, and that corresponds to CD and to DA. It also corresponds over here to FE or EF, depending on whether you want to say that this triangle is upside down or whether you're looking at this triangle over here. Either way, those are the exact same side lengths. Now looking at the last set of angles, here we have angle CAB, and that's the same as this angle right here, DAF. It's also the same as this angle up here, CDE, this one down here, EFB, and finally this one over here, DEF. Or sorry, we'll write it as FED because we do want to go in the same order, right? Because this is upside down of this, so this was CDE, and so this would be FED. Okay, so now that we've warmed up and figured out how to identify any corresponding sides and corresponding angles, let's take a look at a sample problem. In this situation, Tyler, who is 1.6 meters tall, is walking away from a lamppost that is 6 meters tall. When Tyler's shadow measures exactly 4.1 meters, how far would he be from the lamppost? Now, in a situation like this, my recommendation is always to start with a diagram. So before you pause the video and keep going, or I guess pause the video right here and see if you can draw a diagram, but stop once your diagram is complete. So I tried to do this, and this is the diagram I sort of ended up with, right? So I have a person, this Tyler, he's 1.6 meters tall. He's walking away from this lamppost, and the lamppost is 6 meters tall, and Tyler's shadow is 4.1 meters. Now, obviously, this is not to scale. This is not 6 times or 3 times as tall as Tyler, but that's okay. It's just a quick little diagram, okay? We are trying to find out how far Tyler is from the lamppost. So I'll say that's the variable that I'm trying to find out. So as always, I'll put in a let statement. Let X represent Tyler's distance from the post, and that's measured in meters. Always put your units there as well. So pause the video here and see if you can find out what the value of X is. Okay, let's see if we can take this up together. So one thing to recognize is whenever there is light shining, that's what creates a shadow. And it shines directly onto Tyler, creating a shadow sort of like this, right? That lamppost, the top of the very tip of the shadow is sort of where the light hits the tip of Tyler's head and is not able to reach the ground right there, right? That's what a shadow is. It's Tyler blocking the path of the light to the ground. And when you have a situation like this, we actually have a similar triangle. We have a small triangle over here, and we have a larger triangle over here. That's very similar to the first diagram we saw in that Minds On activity. Now, because we know that these two triangles are similar, now we can say, okay, well, if Tyler's 1.6 meters tall, I must have multiplied that by some number to get 6, and therefore I can do that with all of the sides. This is the scale factor. So in an equation, if I basically took 1.6 and I multiplied it by n, I should get 6 meters. So this will allow me to find out what the value of n is. What is that scale factor? To do so, I'll just do the opposite of multiplication. I'll divide both sides by 1.6. And 6 divided by 1.6, it turns out, is 3.75. And so if I want to find out all of the other corresponding side lengths, I can take this side length and multiply it by 3.75, just like so. So here I have the smaller triangle, here's the larger triangle, and I know I multiplied by 3.75 to get from 1.6 to 6. So if I take this smaller side, which is 4.1 meters, and I multiply it by 3.75, I should get this entire side. But this is not the value of x. Notice that this is x plus 4.1. So if I took 4.1 times 3.75, I get x plus 4.1. But this is pretty easy to solve, right? All we have to do is subtract 4.1 from both sides. And now if I evaluate the left side, I get 11.275 equals x. So 11.275 is Tyler's distance from the post in meters. In a nutshell, Tyler's 11.275 meters from the post. Situations like casting shadows, they naturally create similar triangles, but similar triangles pop up all over the place in real life. If you have a pair of known corresponding sides, you know how long they are, you can use that to establish a scale factor, and then you can use the scale factor to find every other side length. In this example, Annie is a surveyor who wants to measure the width of a river, but can't get across the river to sort of place another stake to maybe put a rope across. That's not really doable at this point. So what Annie does is she stands at point A and notes point B directly across the river, sort of like this. Then she walks parallel to the river. She walks 60 meters to point C. And because she was looking directly across the river and walked parallel to the river, that created a 90-degree angle. Now, from here, she walks 5 meters directly away from the river to point D. And again, that creates another 90-degree angle. And now from point D, she looks directly at point B. And she notes that the line that she is looking at, it crosses her path that she walked along the river at the 45-meter mark. So right over here, this distance is 45 meters. Using this information, can you figure out how wide the river is? In other words, what is the length of AB? Pause the video here and see if you can solve it for yourself. All right. So in this case, recognize that because Annie walked 45 meters, or sorry, 60 meters from A to C, and this distance was 45, well, then the remaining must be the last 15 meters, because 45 plus 15 would give you 60. And knowing this, now I know that I've got a triangle here and I've got a triangle here, and these triangles actually are similar because these angles are the same and these angles are the same, which must mean that this angle is the same as this angle. And two triangles with the same angles must be similar to another. So let's see if we can figure this out. Here I have two triangles, and let's move them, and I'm going to redraw them in this blank space. Okay, so in this case, triangle CDE is similar to triangle ABE. And therefore, there is a scale factor. There is some number that I multiplied 15 by to get 48. And maybe you can guess what number this is already. And we can use that number to multiply 5 by to find out this length right here, which is the width of the river, AB. Now, I can probably tell that this number is 3, but just in case it's a little bit harder to guess, we can always say 15 times n got us 45. And if we divide both sides by 15, we'll see that n is actually equal to 3. So we'll confirm that. And doing so, we can say, okay, 5 times 3, that'll get us the width of the river, and that is 15. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.